Cool. So I thought we'd just do a couple more step questions from some fairly recent step 2 papers. They're both integration questions, which seems often the case for question number 1. And I like integration, so that seems all good. Let's do 2020 first, which says by using this substitution here, let's do this integral here. Well, that doesn't seem too bad. This can be written as 1 minus u to the minus 1, of course. Dx is therefore minus 1 times. Where's this minus gone? Oh, because of course then the derivative of 1 minus u is also minus. So the minuses cancel, you just end up with this. Cool, that's fine. We can also write, I guess, we need x, which is just this one there, so that's going to go in there. We need x minus 1, so take away 1 from both. And then this is 1 minus u over 1 minus u. 1 minus 1 minus u just makes a plus u on top. So that goes in there. This goes in there. This dx is replaced with this. Let's do all of that. This seems okay because now what we can do is, and there's lots of different ways you could go about this, but I think I put this one on top and then broke this u to the half out. And also because that leaves behind a 1 over 1 minus u, I can just replace that with a minus half. But now I can think of this minus half as going to the top, which adds to this 3 over 2 to make a 2. And because this guy is a minus 2, they're going to cancel out when you do that. And you're just going to literally end up with the integral of u to the minus a half, which is 2 u to the half. And then, of course, u, we never actually wrote. So, okay, we need to go from here, I guess. 1 over x is 1 minus u. Swap those two things over, we get this. This is x over x. That makes x minus 1 over x. And we can put that in. Interesting to note that the substitution in terms of u, they've disguised it here, but in terms of u, the substitution is this one over this one. So when we get to this next integral, and it's just exactly the same setup, but with two different things here, it seems worth trying just this one over this one as our u substitution. So that's exactly what I did. I did this one over this one. We can use some quotient rule to differentiate that to get dx, which I'll then, I mean, this is x minus x, so that makes minus 3, and then we're going to, or you just write it twice for absolutely no reason. Okay, sure, and then we flip it over, and we end up with this here. So that all seems good. That's ready to go in there. And now we do need x plus 1 and x minus 2. I was a bit lazy here and never actually wrote this in terms of x, because what I figured you could do was I figured I'll just leave the x minus 2 here, and now this x plus 1 I could just write as u times x minus 2. And then when I expand this out, I'm going to get u to the half and x minus 2 to the half. But x minus 2 to the half times x minus 2 to the 3 halves is x minus 2 to the 2. And that will cancel with this x minus 2 to the 2, which was coming from the derivative part of it. So that's fantastic. Pull out the minus a third and cancel these things. It becomes the same integral we saw before. We put this substitution back, and we end up with our answer there, which is great. And now we have one more integral to do, which has 3 things on bottom. So I was a little bit confused as to what to do, but I decided to just go with the same substitution we made before. This I just couldn't be bothered to deal with. This was the first thing I tried, just this over this. Just see how it goes. Why not? So I decided to do a bit of rearranging here just to get this in terms of x, which happens to be the same thing, which is kind of interesting. And then I can work out dx. Again, I used quotient rule here, so it was, what is even is quotient rule? It's f over g is g squared here, and then f dash g here. F dash is just 1, obviously, and then minus g dashed f, which is all that. Okay, fine. So that turns out to be that, which is kind of nice. So that's ready to go into this bit. And now we can try and substitute out all of the rest. We do need this 3x minus 2 business. So times this by 3, and then take away 2. And okay, well, this is, I've put most of this in there already, but let's just focus up here for a second. Times this by 3 here, we get to here. When we take away 2, we're going to end up with, well, you can think of the take away 2 as minus 2u minus 1 over u minus 1. So that's 3u minus 2u is just u. And then minus 6 minus 2 is minus 4, I think. So I think we're going to end up with u minus 4. I never actually wrote that anywhere very clearly, so apologies for that. But it's going to be u minus 4 over u minus 1 is what all that turns out to be. And then the other one was, and I was quite lazy here as well, I said x minus 2 I could just write as, sorry, x minus 1 I could just write as x minus 2 over u. So I was being very lazy here, trying to find ways of cancelling stuff without actually doing any work. So yeah, this continues down there to make this, which is not this thing. This thing is x minus 2, which I then decided how to get rid of. So x minus 2 is just this minus 2, which is this minus 2u minus 2 over u minus 1, I guess. And you end up with this here. So that's just coming from there. So okay, let's substitute those things in as well, and we end up with this, which looks like a complete mess. But I think it works out just about okay because this u and this u will cancel out. So this whole thing is just 1 over u minus 1, which is great. Now this thing here, you can say here you've got u minus 1 and u minus 1 both to the power of half. So that's just one of them, which so those two things there have just become this object here. This bit there has gone there, and then this bit there has gone there. And I've also put in that substitution from earlier of the dx du business. That's all going in there. That's fantastic. So that's all good. And now, of course, 1 over u minus 1 times 1 over u minus 1 times u minus 1 squared, that just all cancels out. So we end up with this. And okay, so now they're both to the power half, so we can expand out. I should have mentioned actually these ones and zeros. Sorry, I've forgotten to mention that. So the ones and zeros have changed. Or the 2 and the infinity have changed because, of course, when x was 2, or is this easier to think about the other? Sorry, it's easier to think about from here, isn't it? When x was 2, u becomes 0, clearly. So that's there. And when x is infinity, infinity minus 2 over infinity minus 1 is basically 1. So that's just 1 there. So that's where that substitution came from. Apologies, should have mentioned that earlier. Anyway, we were back to here. Let's multiply these two things together because they're both the power of a half. We get this. Now, 1 over a quadratic to the power of a half is just an integral you should be aware of. If you complete the square on the quadratic, which is what I'm doing here, you have this result, which is very helpful to you in the formula book. So 1 over root a squared minus x squared it integrates to arc sine x over a. And this is 2 squared minus u minus 2 squared. The fact that it's u minus 2 here doesn't matter at all because it's just like a linear substitution from here. So we can say this just integrates straight to arc sine u minus 2 over 2 because a is 2 here. Between 1 and 0, of course. And then when we put in the values there, we get this arc sine of minus a half. The closest thing to 0 to that is minus pi over 6. And then arc sine minus 1 is minus pi over 2. Just knowing your exact values here, I guess, is necessary. And we end up with pi over 3, which is the answer they wanted us to get, which I think is that question done. Not too easy, that question, particularly part B, or sorry, part 3. Not the easiest thing ever. There's probably much easier ways of doing it than what I did. But what I did, I think, just about worked. So I kind of just went with it. Anyway, I thought this question was great. Loved all of this. This was fantastic and not too tricky either. I thought it was really interesting. Anyway, it's asking us to integrate one of these two things by parts. Now that doesn't look fun to do by parts. The only thing I could really think to use is a 1 here. I guess you could just use the 2, couldn't you, and try and integrate that. But that doesn't seem helpful. This seems much better. The reason it seems much better is because there's way more ways you could split this up into a product of two things. And the most obvious thing to do to me would be to split it into x times 3x squared. And the reason that's obvious to me is because this thing here is now just a beautiful reverse chain rule integral because the derivative of 1 plus x cubed is 3x squared. So we can just integrate this guy to make this. This 2 comes from the fact that it has to cancel out this half when it comes down. And then the half goes down to a minus half, which is where this is, and then the 3x squared comes in, and you get this perfectly. So when you integrate this guy here, you get this. Now, in case you don't do integral by parts the way that I do it, this is the way that I do it. You just integrate one of them, the one you want to integrate, which is this one, and you do that a couple of times, once there, once there. Then you leave this guy alone and put him here, and then you differentiate him over here, which is, of course, a 1. I don't need to write it. And then you slam a minus integral in the middle of them. And now this looks really interesting, right? Because this integral isn't easy to do. However, it is the integral that was right there, that we were sort of considering earlier. So this is really interesting. What you can write is you can write, well, therefore this integral is equal to this one minus this one. But then if you add this integral to both sides, because it so happens just to match this one here exactly, you can just say, well, bring the integrals together, and you just have exactly what they wanted us to integrate, and we just have this thing here. It's really fascinating, really cool. Put a plus c down there, I guess, as well. But no, just a really cool little method. So part 2, of course, is, well, how can we hammer in that method into part 2? Well, this is two things added together, right? We can just expand the brackets and we get this. So again, let's do the same thing. Let's pick one to do integral by parts on and sort of hope, just like in the one before, that the other integral that's formed by parts is the other thing that we were supposed to be integrating in the first place. So okay, let's pick this one to start with. Now, I don't want to integrate 1 over x, so that means me logs, and I'm trying to aim for this thing, right? So let's not do that. Let's integrate sine and differentiate the 1 minus x. So okay, sine integrates to minus cos, and we'll leave 1 over x alone, which is this. And then we'll take away the integral of x to the minus 1 differentiates to minus x to the minus 2. That integrates to minus cos still, so a bunch of negatives cancel. But we end up with this thing here, which is not the thing that I was trying to get to, right? So that's not that great. But what's nice about integration by parts, you can always do it twice. You can always do it twice, baby. Let's just do it twice. Let's just integrate cos again, which goes straight to sine. And let's leave this one alone the first time, and then differentiate it the second time, and boom, there it is. There is finally the integral of the other thing that we were trying to integrate. So when we simplify this up a little bit, we'll end up with the integral of sine x over x is all of this. But then we add this integral that we have not actually found the answer to yet to the other side. And that there is perfectly what they wanted us to integrate in the first place. And so we have this answer here. Again, I've tagged a plus c on the end just for fun. So I just thought it was great. Really, really nice questions. But anyway, part 3 is then going to continue with some other stuff. So we've got y equals e to the x over x to do. Just asking us to sketch it, I guess. So okay, firstly, differentiate. I've used quotient rule again here because I'm a baddie. But anyway, we're going to set that equal to 0. Obviously, x squared. It doesn't matter. We want this to be 0. And factorize it out the e to the x because that can't be 0, and therefore x equals 1. And y equals e is going to be our only stationary point. Get out some axis. When x is massive, e to the x is going to be much bigger than x, so it's going to tend to upwards like this, going to go up like that. When x is massively negative, e to the minus a really big number is basically 0. But then divide by a negative number, even if it's very small or very large and negative, is going to bring it to the negative side of the axis. So it's going to be 10 to 0, but from this side. We've also got an asymptote, of course, at x equals 0. And we need to think about the behavior either side. When we're in the positives, we have a positive over a positive. So that's going to be, it's going to tend the asymptote upwards. And when we're on the negative side, we have a positive over a negative. So it's going to tend to the asymptote from the negatives. And we finally have that stationary point we mentioned before. And so this curve, it's going to be hard to do in PowerPoint. So I'm just going to put it on GeoGebra here. Is right there. Just goes from there and then goes down like this. And that will be our sketch. All done and dusted. Find A if this thing is true. Now, this is where you have to remember the stuff we've done before, because we can turn this question, rather than to the equality of two integrals, let's just turn it to one integral equaling 0. Because this looks quite a lot like that integral we did just a couple of minutes ago, where we had sines over powers of x. So this seems like something that we should be doing using the exact same method. So that's exactly what I did. Let's pick this integral to start with, and let's integrate by parts. Again, I'm going to integrate the e to the x, because that gives me lower powers of x's, which will match with this one, which is fantastic. It actually works out brilliantly. It does it basically immediately. So you end up with the integral of the thing that you want just being e to the x over x, which is fantastic. Because then we can just say, well, the integral, therefore, between 2a and a is just this evaluated between 2a and a, which we can just put in. And then, of course, we can times everything by 2a to get this, I think is what I did, and then factorize out an e to the a, which is never 0, and we get a to the a minus 2 must be 0, which means a is log 2, and that will be the answer to this here. So it's not possible to find distinct integers m that does that thing that we just did. Well, okay, this is the key. Nothing is going to change here with the m and the m's until you can just jump to this line, right? Or essentially actually just this line. And you can put in, instead of 2a and a, just put in n and m, and we'll end up with this thing here. Now, I was a bit unsure how to do this, so I kind of blacked it. I'm not sure whether I got 4 marks. I kind of did this times everything by m, n, and then moved them over and sort of cross-divided to get this. And then I sort of tried to argue that n over m is a rational number, because m, assuming that m and n are integers, of course. And e to the power n minus m is not a rational number. It's an irrational number because it's e to the power of a positive integer. Now, I actually don't know whether that's true, but I was trying to blag it, and that was the best I came up with. Then I looked at the mark scheme, and it's got a slightly nicer way of doing it, based, of course, on something that we've done previously in this question, which is this graph here, which is the graph of e to the x over x, of course. So what the mark scheme argued was, if you want two of these things to be equal, of course, like pick x as 1, you get to here, right? So if you want that to be equal to another input, well, it can't be. There's only one time this graph is ever there. However, if you pick x as 2, you get to here, and there is another time that graph is equal to a position here, which is right there. except that that's in between 0 and 1, not a distinct integer, right? So therefore, what we can argue is, well, okay, there's loads of integers here which give us all these values here, and they are not unique. They're the same as values over here, except the values over here are always between an input of 0 and 1, and therefore not a distinct integer. So the graph tells us that this can never happen for two distinct integers, which is really interesting. I don't actually know whether my proof works. I don't know whether e to the power of an integer has been proven to be always rational or not, or sorry, irrational or not. And I certainly can't do that proof, so maybe I lost a mark or two there. Who knows? Anyway, that was quite a nice little proof that they came up with. Thank you for watching. Some really nice questions there, and I'll see you next time.